All right. This next solution problem is not as straightforward as the last one. When we add our vectors, they are not perpendicular to each other, so we can't treat our resultant as the hypotenuse. However, we can add our vectors using components like we saw in the vector adding activity that we did before. We are still looking at the fact that relative motion of our boat relative to the ground is equal to the speed of the boat relative to the water plus the speed of the water relative to the ground. In order to get this, we're going to need to deal in vectors that are perpendicular to each other. So we know that we can find the x and y components by adding x and y components. So the velocity of the boat relative to the ground in the x direction is equal to the velocity of the boat relative to the water in the x direction plus the velocity of the water to the ground in the x direction. The same thing does apply for the y. Velocity of boat ground y is equal to velocity boat water y plus velocity water ground y. And that is the strategy that we are going to use in order to solve this particular problem. So we are given the fact that the velocity of the boat relative to the water is equal to 6.1 meters per second at 25 degrees upstream. All right, so we see that 25 degrees upstream because the water is going this way and our boat is going a little bit up and over. All right, so we're going to go ahead and break this into our x components and our y components. So velocity of our boat relative to the water in the x direction. Because we already have some equations established for us, remember that our x is equal to r times cosine of theta and our y is equal to r times sine of theta. So our x is going to be equal to our 6.1 meters per second times cosine of 25 degrees. Gives us 5.5. All right, then our v boat water y is this one. .6. Oops. All right. So we have our x component for the boat and the boat to the water and the x component, the boat to the water and the y component. Now we can go ahead and look at the velocity from the water to the ground. All right. We are looking at the fact that it is 1.4 meters per second, and it is entirely downstream. All right. As a result, we are going to see the fact that our x component is 0. We don't have any across for this. It's just straight or down, straight up and down. All right. Oops. Now, velocity of the water to the ground in the y, we do have a value. Our upstream we went ahead and took as positive, so our downstream needs to be negative to make sure that we see that little bit of difference going on there. All right, so we have our velocity of our boat compared to the water broken down into its components, the velocity of the water compared to the ground broken into its components. We can now find our total components. So velocity of the boat to the ground in the x direction is the velocity of the boat to the water in the x direction plus the velocity of the water to the ground in the x direction. That's equal to my 5.5 meters per second plus 0 meters per second. Gives us a total of 5.5 meters per second. Velocity of the boat to the ground in the y direction is equal to the velocity of the boat in the water in the y direction plus the velocity of the water to the ground in the y direction is equal to my 2.6 meters per second plus my negative 1.4 meters per second. That does give me a total of 1.2 meters per second. So now I have my x component, I have my y component. We can go ahead and look at my magnitude and direction. Remember, magnitude is equal to r square root rx squared plus ry squared, and my direction is equal to my inverse tangent of my ry divided by rx. So, velocity boat ground is equal to square root of velocity boat ground x squared plus velocity boat ground y squared. We're looking at 5.6. All right, then we can do our last bit of our direction. See an angle of 12 degrees upstream. Right, I know that's upstream because my y component, my total y component ended up being positive, so that went ahead and told me that it was up. So my speed and my direction, and that is how you solve that.